Okay, so now in the previous video, we are looking at the experiments that we can use, or the experiment that we can perform to determine the partition coefficient. Okay, determine the partition coefficient of solids between different solvents, which solids can be acidic, which can be basic or alkaline, and which can be iodine. So in this case, let's look at the examples of the questions under that. So examples, number one, in an experiment, to determine the partition coefficient, of ammonia between water and trichloromethane (10 cubic centimeters) of the aqueous layer required 13.2 cubic centimeters of 0.25 molar hydrochloric acid for complete neutralization. Then 25 cubic centimeters of trichloromethane layer required 6.60 cubic centimeters of 0.05 molar hydrochloric acid for complete reaction. Calculate the value of partition coefficient KD. Let me abbreviate it as KD. Of partition coefficient KD. Now, they have given us a set of procedure in that in an experiment to determine partition coefficient of ammonia between water. So when you're writing your formula, we'll say concentration of ammonia in water over concentration of ammonia in trichloromethane, because they have brought water first. Now, 10 cubic centimeters of aqueous layer required 13.2 cubic centimeters of 0.25 molar hydrochloric acid for complete reaction. Meaning that our solid is ammonia, our solvents are water and trichloromethane, and our standard solution is hydrochloric acid. So we can first get the number of moles of the standard solution, number of moles of hydrochloric acid. So you'll be saying that if 1,000, because they were given molarity, if 1,000 cubic centimeters contains 0.25 moles, what about 13.2? So we need to first get moles of hydrochloric acid. But anyway, all we are doing, we are trying to first look for the concentration of ammonia in aqueous layer. So we need to first get moles of HCl. Moles of HCl will be equaling to 13.2 times 0.25 out of 1,000. Is it okay? Is it okay?
Yes, it is 3.3 times 10 negative 3 power negative 3.
3.3 times 10 to the power negative 3 moles. We've gotten moles of hydrochloric acid, so we can now get moles of ammonia because hydrochloric acid reacts with the ammonia. So we shall write and say ammonia aqueous plus hydrochloric acid. Aqueous gives us ammonium chloride aqueous. Since we have moles of hydrochloric acid and the reaction ratio is equals 1:1, it means that moles of ammonia are equal to moles of hydrochloric acid, and therefore moles of hydrochloric acid are equal to, okay, moles of ammonia will be 3.3 also times 10 to the power negative 3 moles. Now, after having gotten moles of hydrochloric acid and moles of ammonia, now we can get the concentration of ammonia in aqueous layer. Remember, they said that 10 cubic centimeters of aqueous layer required 13.2 cubic centimeters of 0.25 moles of hydrochloric acid, which yielded 3.3 moles of ammonia. So it means that 10 cubic centimeters, we're going to write and say that 10 cubic centimeters of aqueous layer contain 3.3 times 10 to the power negative 3 moles of ammonia. You first get moles of ammonia, then you see what does the aqueous layer contain. So what about 1,000? Because we need the concentration of ammonia in aqueous layer. So concentration of ammonia, we shall solve aqueous layer contain 3.3 times 10 power negative 3 times 1,000 out of 10. We shall get moles. So this one will give us 0.33 molar. This is the concentration of ammonia in aqueous layer. Is it clear? Is it clear?
Yes.
Now, after that, now we go to this part of organic layer. They're saying that 25 cubic centimeters of trichloromethane layer required 6.6 of 0.05 molar hydrochloric acid. So let's first get moles of hydrochloric acid for the case of organic layer. So that was aqueous layer, it's done. So now we are going to concentration of ammonia in organic layer. So we need to first get moles of hydrochloric acid. If 1,000 moles contain this, what about 6.60? So moles of hydrochloric acid will be 6.60 times 0.05 out of 1,000. And this is going to be 3.3 times 10 to the power negative 4 moles. But because moles of ammonia and moles of hydrochloric acid are the same, still moles of ammonia will be equaling to moles of hydrochloric acid, which is equals to 3.3 times 10 power negative 4 moles. Now, these are moles of ammonia in organic layer, but they're saying that 25 cubic centimeters of trichloromethane, which is the organic layer. So you will say that 25 cubic centimeters of the organic layer contain 3.3 times 10 to the power negative 4 moles of ammonia. What about 1,000? This one will give us the concentration of ammonia in the organic layer. So it will be 3.3 times 10 to the power negative 4 times 1,000 out of 25. You need to show all these statements here where I've put a line. You do it from first principles, show all the statements. So this one will give you 0.0132 molar. So now this is the concentration of ammonia in the organic layer. So you have the concentration of ammonia in aqueous layer, and you have the concentration of ammonia in the organic layer, but they want Kd. Are we together there so far?
Yes.
Good. So now what we do, we are going to go ahead and say that the Kd is equals to concentration of ammonia in water layer or aqueous layer out of concentration of ammonia in the organic layer, which is the trichloromethane. Even if you use aqueous and here you use organic, no problem. So it is going to be 0.33 divided by 0.0132. And it's going to be equaling to 25. So our Kd is 25. Is it okay?
Yes.
Okay. If that is okay, then let's see this. Let's do this second example. 50 cubic centimeters of 1.5 molar ammonia solution was shaken with 50 cubic centimeters of trichloromethane in a separating funnel. After the layers had settled, cubic centimeters of trichloromethane layer was pipetted and titrated with 0.05 molar hydrochloric acid, 22.90 cubic centimeters of the acid was required for complete neutralization. Calculate the value of the partition coefficient. That is the question we are having. That is the question that now we are having. That is the question that we are having. 50 cubic centimeters of 1.5 molar ammonia solution was shaken with 50 cubic centimeters of trichloromethane in a separating funnel. After the layers had settled, 20 cubic centimeters of trichloromethane layer was pipetted and titrated with 0.05 molar hydrochloric acid, saying that this volume of the acid was required for complete neutralization. Calculate the value of the partition coefficient or the distribution coefficient. Well, for this case, if we can begin with the concentration of ammonia in the organic layer. Why? All the information given is about organic layer, meaning it is the one that will give us that we can get first, and then maybe we get the one of aqueous layer by subtraction. Because since you have the concentration of the whole solution that was shaken, if you get the one of organic layer, then you can get the one of aqueous layer by getting 1.5 minus the one in organic layer. Is it okay?
Yes.
So we are going to first get moles of hydrochloric acid. Because I'm saying that 50 cubic centimeters of trichloromethane, okay, after the layers are separated, 20 cubic centimeters was pipetted and titrated with 0.05 molar hydrochloric acid, but 22.9 of the acid was required for complete neutralization. So if these ones are in 1,000, what about in 22.9? So moles of hydrochloric acid will be 22.90 times 0.05 out of 1,000. And these are going to be 1.145 times 10 to the power negative 3 moles. And from the equation, where we have ammonia reacting with hydrochloric acid, produce ammonium chloride. Oh, no charge, ammonium chloride. To mean that moles of ammonia NH3 is equal to moles of hydrochloric acid, and those are equal to 1.145 times 10 to the power negative 3 moles. But they are saying that 20 cubic centimeters of trichloromethane is the one which was pipetted and titrated with this, meaning 20 is the one which reacted. So we shall say, if 20 is the one that reacted, what about in 1,000? Isn't it? To get the concentration. So these are the moles of ammonia in the organic layer. So we shall say 20 of trichloromethane that was pipetted. If 20 is the one that reacted, 20 cubic centimeters of organic layer contain 1.145 times 10 to the power negative 3 moles. Then what about 1,000 cubic centimeters of the organic layer contain 1.145 times 10 to the power negative 3 times 1,000 out of 20 moles. And this is going to give us the molarity as 0.05725 molar. So this is the concentration of ammonia in the organic layer. Now, initial concentration of ammonia, okay, initial concentration of ammonia, remember, is equal to 1.5 molar. And this initial concentration of ammonia, since it's a solution, it means that it is the initial concentration of ammonia in aqueous layer. Because it was ammonia solution. You can't form solutions without adding some water. So it is initial concentration of ammonia in aqueous what? In aqueous layer is 1.5. Now, since you have the one in organic layer, then you must be having the concentration of ammonia remaining in aqueous layer. And that would be 1.5 minus 0.05725. And this is going to give you 1.44275 molar. But they want us to calculate KD. And you know that your KD is the concentration of ammonia in water, because they said that calculate the value of calculate the value of partition coefficient. But it was ammonia solution, then shaken with the trichloromethane. So we begin with water and then over tetrachloromethane, which is CHCl3. Trichloromethane is CHCl3. So it is going to be ammonium in water, that is 1.44275 divided by the one in organic, which is 0.05725. And thus the KD will be 25.2. Is it okay, Sebo?
Yes, it is okay.
I'm going to do my final question, and then I surprise you with an exercise. Okay. And my fine example is a bit lengthy. It is number 3, and part A is iodine in aqueous potassium iodide was shaken vigorously with an equal volume of tetrachloromethane. State the role of potassium iodide solution. 2, state and explain the observation. 3 made in A. Then B, a certain amount of iodine was shaken with 50 cubic centimeters of tetrachloromethane. Allow me to use symbols, tetrachloromethane, and 50 cubic centimeters of water in a separating funnel. .0 cubic centimeters of aqueous layer required 6.70 cubic centimeters of 0.05 molar sodium thiosulfate solution while 25.0 cubic centimeters of organic layer required 27.0 cubic centimeters of 1.15 molar sodium thiosulfate solution. Calculate the distribution coefficient for iodine between carbon tetrachloride and water. Seems lengthy, but it is very easy. It is the same question almost, only that it has got some part A, which needs us to reason here. Okay, so now iodine in aqueous potassium iodide. They want us to make an observation. Now, they want us to first state what the role of potassium iodide is. So for part A, Roman 1, the role of potassium iodide is to provide iodide ions which combine with iodine molecules form a soluble complex of triiodide ions. That is its role. From potassium iodide solution, we get iodide ions, which combine with the iodine molecules to form a soluble complex of triiodide ions. What we mean by equation, iodine molecules combine with the iodide ions from potassium iodide to form a soluble complex of triiodide ions. So that is it that we can have. Otherwise, iodine is sparingly soluble in water, maybe for emphasis. Otherwise, iodine is sparingly soluble in water. Okay, from here, part 2. State and explain the observation made in A. Iodine in aqueous potassium iodide was vigorously shaken with equal volume of tetrachloromethane. Tetrachloromethane is colorless. So the moment you shake iodine, potassium iodide with the tetrachloromethane, this colorless solution of tetrachloromethane becomes purple. In other words, the tetrachloromethane layer becomes purple. So the observation in first state, you need to first state the observation. You first tell me that the colorless solution, the colorless, or you can say the colorless tetrachloromethane layer, tetrachloromethane layer becomes purple. Becomes purple. Then the explanation to that is that the iodine that was making the aqueous layer brown dissolves more in the organic layer. Okay, so the iodine, it's because the iodine that was making the aqueous layer brown dissolves more in the organic layer. Full stop. Then the aqueous layer finally becomes faint. Finally becomes faint brown or pale brown. So basically, that is what we make as the observation. And then part 2 or part B doesn't change from what we have been discussing. Okay, so they are saying that a certain amount of iodine was shaken with 50 cubic centimeters of tetrachloromethane and 50 cubic centimeters of water in that funnel. 25 cubic centimeters of the aqueous layer, so we shall begin with the aqueous layer, required 6.7 of sodium thiosulfate. So sodium thiosulfate is our standard solution. So you can get the moles of sodium thiosulfate, and after getting moles of sodium thiosulfate, we can get moles of the iodine. Okay, and after getting moles of iodine, now we can connect and get every other thing. So you need to move up, you need to move with these notes valid with you. 25 of aqueous layer required 6.7 of 0.05 molar sodium thiosulfate, while 25 of organic layer required 27.0 of 1.15 molar sodium thiosulfate solution. So we need to get those concentrations of iodine in those solvents, and then we calculate the KD. Now, let's first get the concentration. I'm on part B. Let's first get the concentration of iodine in the aqueous layer. Because in the question, they said that 25 of the aqueous layer is 25 cubic centimeters, but it required 6.7 of 0.05 molar sodium thiosulfate. So let's first get moles of sodium thiosulfate. So moles of thiosulfate ions are going to be equal to 6.7 times 0.005 out of 1,000. What do you get? For this case, we shall get 6.7 times 0.05. The answer we divide it by 1,000. You're going to come up with 3.6 0.685 times 10 to the power -4 moles. So after getting these moles, you have to write the equation between thiosulfate ions, as we saw in the experiment, plus iodine. You will get tetrathionate ions, and iodide ions. So you can see that 2 moles of thiosulfate react with the 1 mole of iodine, okay? 2 moles of thiosulfate ions react with 1 mole of iodine. So if 2 moles of thiosulfate react with 1 mole of iodine, what about these moles? So the 3.685 times 10 to the power -4 moles will react with a half of 3.685 times 10 to the power -4 moles. And this is going to give us 1.8425 times 10 to the power -4 moles. So these are moles of iodine in the aqueous layer. So meaning that 25 cubic centimeters of the aqueous layer contain these moles. What about 1,000? So that one will give us the concentration of iodine in the aqueous layer. So we shall say 25 cubic centimeters of the aqueous layer contain 1.8425 times 10 to the power -4 moles. Then what about 1,000 of aqueous layer contain 1.8425 times 10 to the power -4 times 1,000 out of 25. This one will give us moles of iodine in the aqueous layer, and you're going to get 0.00737 molar. You check very well. In the case of any mistake, I'm using the calculator here, so you can check with me and you see. Now, after getting that, now we go to the organic layer. Concentration of iodine in the organic layer. In the question, they told us that while 25.0 cubic centimeters of organic layer, so this is also 25 cubic centimeters of organic layer required, it required 27.20 cubic centimeters of 1.15 molar sodium thiosulfate solution. So it means that I need first get moles of thiosulfate in this layer. So moles of thiosulfate are going to be equal to 27.20 times 1.15 out of 1,000. This is going to give me 1.564 times 10 power -2 moles. From the reaction ratio, 2 moles of thiosulfate react with 1 mole of iodine, meaning that moles of iodine are equal to a half of 1.564 times 10 power -2. And this is going to give us moles of iodine as 1. I interchanged the moles of thiosulfate. Moles of thiosulfate are 3.128 times 10 to the power -2. Then Here we shall multiply 3.128 times 10 to the power -2, and it will give us 1.564 times 10 to the power -2. You change that, I have interchanged the answers. So these are moles of iodine in the organic layer. But the organic layer, they're saying 25 cubic centimeters of the organic layer. So 25 cubic centimeters of the organic layer contain 1.564 times 10 to the power -2 moles. What about 1,000? 1,000 cubic centimeters will contain 1.564 times 10 to the power -2 times 1,000 out of 25. This is going to give you the concentration of iodine in the organic layer, which is 0.6256. So you have molarity in the aqueous layer, you have molarity in the organic layer. But the question is saying that the distribution coefficient for iodine between carbon tetrachloride and water. Now they have begun with the carbon tetrachloride. If they have begun with the carbon tetrachloride, even you on the formula, you're going to say that Kd is equals to concentration of iodine in carbon tetrachloride out of concentration of iodine in water, and it's going to be 0.6256 over 0.00. The one of water was 0.00737. And this is going to be 84.88. That is the KD that we are going to have. Every viewer, I want you to attempt this question. This is 0.9656 grams of iodine was added to a mixture of 50 cubic centimeters of water and 50 cubic centimeters of tetrachloromethane, CCl4. We'll stop. 25 cubic centimeters of the aqueous layer required 4.40 cubic centimeters of 0.01 molar sodium thiosulfate solution. For complete reaction. For complete reaction. 0.9656 grams of iodine was added to a mixture of 50 cubic centimeters grams of water, rather 50 cubic centimeters of water, sorry, and 50 cubic centimeters of tetrachloromethane. 25 of the aqueous layer required 4.40 of 0.01 molar sodium thiosulfate solution for complete reaction. Full stop. Full stop. Full stop. Determine the distribution coefficient of iodine between carbon tetrachloride and water. In brackets, I is equals to 127. Iodine atom is 127, and you should get the answer, which is 85.4. That is the answer that you should get, 85.4. You need to first get the concentration in aqueous, initial concentration of iodine in aqueous layer can be gotten from here, because you dissolved this mass in a mixture of 50 cubic centimeters of water and tetrachloromethane, meaning that 50 dissolved this. What about 1,000? That one will give you the initial concentration of iodine tetrachloromethane, rather in aqueous layer. Now from here, members, we shall be looking at applications of distribution law or the partition law. Okay, and that is where we shall start from next time. I wish you all the best. Thanks for viewing us. I remain hyper. And before I go, let me give a closing prayer. Almighty God, we thank you for the gift of life that you have given to us. We thank you for these children. We thank you for every teacher. We thank you for everyone in the world. And we thank you for having kept us this long. We don't take it for granted that you exist, and we don't take you for granted that you're still providing for us and you're still keeping us in this period. I pray that these students, as they watch these things, they get a clear understanding and they get the clear knowledge about overcoming the questions. I want them to excel, and we are doing all this to make sure that these students excel. So watch over them and be the guide before them. I've been able to pray through Jesus Christ, our Lord. Amen.